Hi, today I will be presenting on the role of system calls in secure process management. This work was prepared by Afaf Albadway from section 3 and Bilal Karadeniz from section 1. We will explore how system calls serve as a critical control point for securing process against modern threats. Let's start with the fundamentals. User space process need kernel services to access privileged resources like files, memory, devices, and network. System calls are the canonical interface, the boundary for these requests. This makes the system call interface a natural checkpoint for enforcing security and reducing the attack surface. Think of it as a gateway where every process must pass through to interact with the kernel. When we assume an attacker has gained control of a user space process, our defense strategy has three primary objectives. First, prevent. We want to stop the compromised process from performing privileged misuse like data exfiltration or privilege escalation. Second, detect. We need to identify malicious sequences of actions and anomalous behavior in real time. Third, contain. We must limit collateral damage and prevent the attacker from pivoting to other parts of the systems. These three objectives form the foundation of our cycle-based defense strategy. To achieve these objectives, we have four complementary defense mechanisms available. Cycle filtering at the top, in-process isolation on the left, interposition monitoring on the right, and authentication cycles at the bottom. This one. Each plays a distinct role, and as we will see, they work best when combined. Let me walk you through each one. Our first defense is SecComp, or Secure Computing Mode, which restricts the set of system calls a process is allowed to make. The workflow is straightforward. When a process makes a size call, we check it against a whitelist. If it's allowed, we process with the system call. If not, the kernel terminates the process. SecComp is widely used in containers, browsers, and mobile platforms to dramatically reduce the attack surface. It's a proven production-ready defense mechanism. The second defense involves placing a monitor between a process and the kernel to observe, log, or redirect system calls. This is the foundation of many behavior-based malware detection systems. It allows for flexible policy enforcement and runtime detection of anomalous syscall sequences. The monitor intercepts the syscall, analyzes it, and then forwards it to the kernel if appropriate. The third defense augments the kernel interface to verify origin and intent of a system call. It uses cryptographic annotations or capability tokens to ensure only authorized code paths can request privileged operations. This aims to prevent confused deputy attacks, where a privileged program is tricked into misusing its authority. Think of it as adding a seal of authentication to each cycle. My friend will continue.
Our first defense companions light out and process isolation such as ERM using into MPCAR with cycle hooks that this protective sensitive data and first privileged inside process without overhead of a full sandbox. Measurable impact. Now let's look at the measurable impact of strong defense. We can quantify three key benefit: attack surface reducing, blocking used cycle, removing entire classes of kernel target exploit. This is measurable and widely adopted in protection system. Both exploit containment even with full memory control. An attacker cannot invoke blocked cycle to pivot scout or open raw devices behavior dedication ensuring cycle sequence successfully enabled to decay of malware patterns such as runs more encrypted loops. These aren't theoretical benefits, they are proven in real world deployments. However, no defense is perfect. We face three main practical challenges. Policy management is hard, manual testing is error-prone, and personal automation tool help, but must balance security versus feature adding complexity. Evasion is possible. Attackers use semantic gaps, obscure cycle, and API fiction to hide malicious intent from mentors. Their cost-heavy weight mentoring impose performance overhead, while overly strict filter can break legitimate application behaviors. These are real-world contexts we must address. Let performance overhead. Let's talk numbers. This chart show performance overhead relative no performance overhead relative no protection across various SPCK benchmark. The key takeaway note of a lower overhead of modern in-process isolation technique like ERIM, different protection scam, CBS, ERM, CPI show varying overhead, but modern approaches like ERM significantly reduce the performance cost for most benchmarker. The overhead is modest through some workload like 400,070 show a higher impact. The important point is the security has cost, but modern technique can minimize it. Defense in-depth strategies. This brings us to crucial point. The C-cycle control are one layer in defense in-depth. Maximum effectiveness is achieved when cycle-based control are combined with other defense, and as the center we have cycle filtering with scam, reducing kernel attack and server moving outward, memory safety and SFAI preventing initial exploit. Next, in process isolation protects secrets. Finally, the outer layers provide cycle monitoring and automatically dedication respond to incident. Each layer refers the other, creating comprehensive security posture. Looking forward, we have three key research. First, automatic explained policy synthesis. How can we produce minimal, correct, and human understandable cycle policy automatically? Second, resistance to API function. How can we build defense that are rely on semantic behavior model, not just fixed cycle signature? Third, hardware assistant kernel access control. How can we extend fine grained hardware protection to mediate kernel access with low overhead? To conclude, the system call interface is a strategy control point. It's enable powerful attack surface, reducing containment and behavior dedication. While not server-bound, its value is proven in practical deployments. The best results come from integrate strategy, combining cycle control with issues with memory safety and integrity. Modern system core represent fundamental protocol and control them effectively, essential for modern system security. Thank you so much for listening and paying attention.